Hi everyone, welcome to the GATE lecture series of ENGG.COLLEGE. College. I am Dr.S.BHUVANESWARI, Associate Professor, Department of EEE. Today's topic is three-phase circuits. So this three-phase circuit is coming under the electric circuits for electrical engineering. So here in today's topic we are going to discuss on the polyphase circuits, three-phase circuits and balanced unbalanced system, three-phase connections and its types, phase sequence, and finally we are going to solve a gate question. So this is the AC voltage equation. The sinusoidal voltage can be given by the expression V of t is equal to Vm sin omega t plus 5, and here Vm represents the amplitude of the sine wave and omega represents the angular frequency in radians per second, phi represents the phase and t represents the time in seconds. And you can see here this is the waveform of the AC voltage given by its expression Vm sin omega t plus 5. First, we need to know what is a polyphase circuit. When there are multiple sources are present in a network, if it has a same amplitude frequency and with a different phase, then it is termed to be polyphase circuit. And now the sinusoidal voltage can be measured in degrees, so it is completely measuring 360 degrees cycle. And here when there are n sources present in a polyphase circuit, then the phase difference between each phase currents or voltages can be given by the relationship 360 divided by n. Here n represents n represents the number of sources. If we assume there are 3 sources, then 360 divided by 3 so the phase difference between each voltage or each current will be 120 degree. So this is a formula to calculate the phase difference between each voltages, each source voltages or each source currents. And we have seen the definition for polyphase circuits, and this is the definition for a three-phase circuit. So when there are 3 sources in a circuit or a network, then we call that as a three-phase circuit. It can be defined as a three-phase system is a system produced by a generator that includes 3 sources that contains the same amplitude, same frequency, and they are out of phase by 120 degree. So in the previous discussion, as I told you, if there are 3 number of phases, they will be displaced by an angle of 120 degree. So that is the definition. So the phase difference is 360 divided by 3, which is 120 degree is the phase difference between each phases. We need to know what is the need for a three-phase circuit. Basically, we can equate a three-phase system, a single three-phase system with 3 single-phase system. So when we compare those two, we have lot of advantage for going with three-phase circuit. The first and foremost advantage is when we have a single three-phase power system, then the power rating achieved through that system is going to be equivalent to a 3 times power rating of a single phase power. So that is the main advantage. And here one 3-phase generator is more economical than a 3 single phase generators. So the cost wise also, the generator cost is also getting reduced. So to achieve the same amount of power rating, we need 3 generators in case of a single phase system and a single 3-phase generator in case of a 3-phase system. So that is one of the other advantage. And 3-phase system involves a maximum of 4 conductors. So if we go with a 3-phase system, we need at least 4 conductor, and maximum along with the ground conductor we need 5. But when we go with a 3 single phase system, it requires almost 6 conductors. So that is a cost involved in this is also getting increased. And then the instantaneous power in a three-phase system is always constant. So these are the major advantage why we go with a three-phase system. So a three-phase system can again be classified into two: balanced system and an unbalanced system. Balanced three-phase system. In a three-phase balanced system, when the phase voltages or currents are displaced from each other by 120 degree. Why? Because the windings of the generator are displaced through 120 degree from each other. So that is the reason we are getting that 120 degree phase shift between each phase currents and voltages. And what are the basic requirements for a three-phase system or a circuit for which it can be called as a balanced circuit? The first and foremost is all the three sources are represented by a set of balanced three-phase voltages or variables. And the next is all loads are three-phase with equal impedances. So whenever the load is also having equal impedances on all the three phases, we call that to be a balanced load. And the line impedances are equal in all the three phases. So these are the three requisites to make a system to be a balanced system. Properties of a balanced system. Here the waveform is perfectly sinusoidal. In a three-phase system, the waveform is going to be perfectly sinusoidal. That is, if we say in terms of magnitude and phase shift of 120 degree. So that is the first property of a three-phase system. And the next is current flowing through each phase is identical. So here each phase is going to carry a equal amount of current. So that is also one of the property of a balanced system. And no current flows through the neutral. Obviously we have three phase currents are equal, then there is no current or the neutral current will be zero. And power loss is also very low. That is also one of the property of a balanced system, or else even the power loss will not be present or it will be very low. Then unbalanced system. A system is unbalanced if either of the source is unbalanced or the load is unbalanced. Say we have the source and load. So source side and load side. So we can see here. So this is the source end and we have the load end. So this side is the source end and this is the load end. When we call a system to be a balanced, means both the ends must be balanced. So that is the actual definition of a balanced system. If any one of the sides is not balanced, which means all the impedances are not equal, all the currents carried by the phases are not equal, then we call that to be an unbalanced system. When equal load is connected across each phase winding, then the current flowing in each phase is equal and the system is said to be balanced. Even most of the cases, the source will be balanced and the load will be unbalanced. This is the waveform of a three-phase voltages or three-phase currents. Here we can see we generally represent the three phase with R, Y and V. So this is the R phase, this is Y phase and this is B phase. For representation we can name it anything. A, B, C, here it is represented as A, B, C. See, R phase is starting at 0 degrees. So the phase is 0 in case of R wave, and B wave is starting after 120 degree. You can see the lag here. So this is the lag. How much of degree is lagging? The Y phase is lagging 120 degree with of R phase. And then what about B phase? Here you can see the B phase is lagging 240 degree with respect to R phase. Otherwise we can call it as 120 degree with the Y phase. So this is the relationship between three phase voltages. So the magnitude is going to be constant throughout and the phase shift alone will be there, and the frequency is common for all the three phases. As we discussed, a balanced system is going to have same amplitude, same frequency, but the difference with them is only the phase shift. So R and Y having a phase difference of 120 and Y and B having phase shift of 120, R and B is going to have a phase shift of 240. How do we represent the three equations what we seen in the previous slide? So we have these three equations. VA, I can represent the first R wave to be VA. VA is equal to Vm sin omega t. Since I am going to take that as reference, my phase phi is 0. So right in the first equation we have seen, we represent the equation as Vm So this is the equation we have seen in the first slide. So here the phase phi, as we take this A phase to be the reference phase, the phase will be 0. So it is Vm sin omega t alone. So when we represent that in the polar form, here we can obtain, and this is the form of rectangular. And the next waveform is Vb. The voltage taken up by the Y phase or the B phase can be given by this equation Vm sin omega t minus 120. Since the B phase lags 120 degree with respect to R phase, it is minus 120 degree. So when we represent the same equation in polar form, we get Vm is equal to Vm angle minus 120 degree, and when this can be represented in the rectangular form, that is given by Vm of cos minus 120 plus j sin minus 120. So this is the equation, and next is the equation of the third wave Vc. Vc is equal to Vm sin omega t minus 240. As I already told you, it is nothing but the B phase and R phase are going to have a phase shift of 240 degree. That is why here we have minus 240. So this can be represented as a polar form in this Vm angle minus 240, and here it is represented with the rectangular form Vm of minus 1 by 2 plus j root 3 by 2. So these are the three equations of a three-phase voltages. And here this is a three-phase balanced circuit. We can see both the source side and load side are balanced, which means the voltages are equal in all the three phases. The current flowing through all the phases will be equal. The impedances of all the three phases will be equal. So this is the case of balanced circuit. So the first diagram shows us when the source and load are both connected in star connection. So this will be seen in the coming slide. And we have even delta connection. This delta connection, both the ways, the load source both are connected in delta connection, and they are connected and they are equal, they are having equal phase voltages, equal phase currents, as well as equal impedances. So before we move on to the different types of connections available in a three-phase circuit, we have to know what is a phase sequence. So phase sequence is nothing but the order in which the voltage waveforms of a polyphase AC source reach their respective peaks. Means so this is the phase sequence. So R phase is taking its peak for the first, and Y phase is reaching its peak next, and B phase is reaching its peak next. So this is the order in which the voltage waveforms of a polyphase circuit, here in this case it is a three-phase circuit, reach their respective peak. Then my phase sequence will be R, Y, B. So this phase sequence I can either call it as a positive phase sequence also. Okay, so this is the positive phase sequence. As I told you, since I have represented with ABC in the other slides, I am going to represent A phase coming or reaching its peak first. A phase is reaching its peak first, B phase is reaching its peak next, and C phase is reaching its peak next. So this is the order in which the respective voltages reaches its peak. So here this is the way of representing a positive phase sequence. See, always we consider the A phase to be the reference phase. So VA can be represented by V angle 0, and after VA, after a lag means always we need to go with the clockwise direction. So this is a clockwise direction. When we go with the clockwise direction of 120 degree, once it reaches the minus 120 degree, this VB is going to take up its 0th position, and after this 120 degree, this is 120 and this is 120. So after VA started, after a phase shift of 120 degree, VB is starting, and after this VC is also starting. So this is the sequence in which the peaks are reaching their maximum. This is the order. So that is why it is called as a positive sequence. And coming to negative sequence. So this is a negative sequence, and this negative sequence says like V is as such kept as reference. Here VC is reaching after VA reaches its peak. This is the next peak, which means we can say like so this is R, guys. This is A, this is C, and this is B, which means after A reaches its peak, the next one to reach its peak is C with a lag of 120 degree. So this is the lag. So this lag 120, VC reaching its peak, and then after this 240, this is 240, so this angle is 240 and this is 120. VB reaches, after VA reaches with a phase difference of 240, VB is reaching its peak next to C. So this is the reason we call this to be a negative sequence. So we need to know what are the different types of three-phase connections available. The first type of connection we call that to be a star connection, or a star or Y or T connection. We can call either of the three ways. And the next type is delta or pi. Here we can see the star connection can be represented like this. It is otherwise called as T connection, as I already told you. This is one where there will be each winding, say A winding, B winding, C winding, all the ends of these three windings will be connected together at a point, and that point is called as a neutral. So this point is called as neutral. So here this Y connection or star connection is represented with A, B, C terminals along with a tied terminal called neutral. In delta connection, when all the three windings are connected end to end, then such type of network formed is called as a delta connection. You can see A winding is connected with B winding and B is connected with C. All three are connected in the form of a delta. So normally we need to know what are the different types of system available in a star connection and delta connection. Here we can see in a star connection we have two possibilities. One is 3-phase 4-wire system and 3-phase 5-wire system. Not only this, we have 3-phase 3-wire system also available in case of a transmission system. This is for the distribution end. The star connection can be available with two different types of connections. These are the 3 phases. Here we have 3 phases along with a 4th wire. This 4th wire is called as the neutral wire. So A, B, C are the 3 phase wires, and there is another wire called as neutral where all the 3 phases are tied together and the common point is termed as the neutral. So this is a 3-phase 4-wire system. Not only this, we have the other system called 3-phase 5-wire system where the ground is going to be included as a 5th wire, delta connection. Always we have 3-phase 3-wire system or also 3-phase 4-wire system in case of delta. Without the presence of ground, we have 3-phase 3-wire system. With the presence of ground, we have 3-phase 4-wire system. The relationship between the phase voltages and the line voltages of a star connection and delta connection. When we measure the voltage across a terminal and neutral, then we call that to be a phase voltage. When we measure the voltage across two different terminals of different phases, then we call that as a line voltage. In star connection, phase voltage is equal to the line voltage divided by √3, and the current through the phase and line both are equal. So this is in case of star. In case of delta, the phase voltage will be equal to the line voltage and the current through the phase is equal to IL by √3. So these are the relationship between the phase and line voltages and currents. So we are going to solve a gate question based on so far whatever the concept we have learned. Now this is a gate question which is asked in 2022. Here we can see in the circuit shown below, a 3-phase star connected unbalanced load is connected to a balanced 3-phase supply of 100 √3 volts with phase sequence A, B, C. The star connected load has a impedance ZA is equal to 10 ohms and ZB equal to 20 angle 60 degree ohms. The value of ZC in ohms for which the voltage across the nodes N and N dash is 0 is given 4 options. So first we need to understand the problem, then we will solve. See, in the question it is given that a 3-phase star connected unbalanced load is connected to a balanced 3-phase supply. So which means this is a balanced 3-phase supply and this is a unbalanced load. So we have the complete system is called as unbalanced, since from the statement it is understood that the impedances of all the 3 phases are not equal. So we must first understand what are the data given in the question and have to find what is the unknown which is asked. So the given parameters in the question are the line voltage given VL is equal to 100 √3. So this is the data given in the problem, and apart from this ZA is also given. ZA is 10 ohms and ZB is 20 angle 60 degree ohms. ZC is the question asked, and one more thing is given, N and N dash are having 0 potential difference, means zero potential difference. So it is meaning that N and N dash are having same potential. Now considering that, we can say like the current through the 3 phases IA, IB and IC together sum up to 0. That is the meaning we need to take out of that. We find the phase voltage. V phase is equal to VL by root 3. So VL is given already 100 root 3. 100 root 3 divided by root 3. So root 3 getting cancelled. V phase is 100. So this is the phase voltage 100 volts. Now we need to find out what is the current through A phase and B phase and C phase. After finding out, we can find what is ZC. A phase is 100 angle 0. Always we need to take up the A phase to be the reference. So it is angle 0. VB phase is equal to 100 angle minus 120 degree. The phase sequence given is A, B, C. That is why it is minus 120 for B. We can call this VC phase as 100 angle plus 120 also. So what is the meaning we have to take out is, this is the voltage plus 120. This is A phase, this is B phase and C phase. We can say B phase is lagging 120 degree out of A and C phase is leading 120 degree out of A. So that is the meaning. We can say in either way, 100 angle minus 240 also we can say, or else 100 angle plus 120 also we can say. IA is equal to 100 angle 0 by ZA is given as 10. So it is 10 angle 0. So this is IA in amperes, and then IB is 100 angle minus 120 divided by ZB. What is ZB? So ZB is 20 angle 60. So it is 20 angle 60 degree. So how can we then, this is 5 angle minus 180. So this 60 goes to the numerator and it becomes minus 60. So minus 120 plus minus 60 is 5 angle minus 180 degree. This is IB. Now we need to find out what is IC. IC is minus of IA plus IB. So this equation we have to get it from here. So IA is equal to minus of IB plus IC, or else IC is equal to minus of IA plus IB. What is the value of IA we got? It is 10. Minus 10 plus IB we got as 5 angle minus 180. When we convert this to polar form, we are going to obtain minus 10 minus 5 plus J0. When we convert this polar form to rectangular, we are going to obtain minus 5 plus J0. And your IC is going to be minus 5 plus J0. So this is the current we are going to get for C phase. So this can again be converted to polar form. So IC can be obtained as minus 5 plus J0. When we convert that to polar form, we are going to get 5 angle 180 degree. So this is the current value we are getting, and when we substitute that in ZC equation, VC phase divided by IC, VC phase is 100 angle 120 degree and this IC is 5 angle 180 degree. When solve this 180, when it goes to the numerator it will become minus 180 and this is minus 60. So ZC value is 20 angle minus 60. So this is the answer. So you can see, so the correct answer is 20 angle minus 60. So this is the right answer for this question. We'll continue the remaining questions in the next video. Thank you.